So, if you look at a standard flat map flying from South Korea to New York, it basically looks like a straight line right across the Pacific Ocean, right?
Right, like maybe clipping California on the way.
Yeah, exactly. But if you actually book that flight, you don't go across the Pacific at all. I mean, you fly straight north, right over the Arctic Circle. So, for centuries, our maps have basically been lying to our eyes.
Oh, they absolutely have. A two-dimensional map. It just simply cannot tell the truth about a three-dimensional world without horribly distorting something along the way.
Which is wild to think about.
It is. The shortest distance between 2 points on a globe, well, it rarely looks like a straight line on paper.
Welcome to today's deep dive, everyone. I want you to think back to that standard world map you grew up with. You know the one?
The pull-down one over the chalkboard?
Yes, exactly, in your third grade classroom. It's this flat rectangle, likely the Mercator projection, and right there, dead center, is Europe, with the Prime Meridian slicing straight down through London.
And we are so used to that specific image of the Earth that it feels, like a law of nature.
Right, it just feels correct.
You look at that map and instinctively feel that the Atlantic Ocean is the center of the world. And why? Well, just because that's where the printer decided to fold the paper in half, hundreds of years ago.
Wow, yeah.
The Mercator map was brilliant for 16th century sailors trying to navigate by compass, sure, but it cemented a very specific, a very Eurocentric view of global geography.
But what if I told you that center is completely arbitrary?
Mm.
We have a massive stack of sources in front of us today. I mean, cartography research, academic papers, and these fascinating mathematical diagrams.
They're really cool to look at.
They are. And they detail how to map the Earth on a 3D Cartesian XYZ coordinate system.
Changing just a few numbers in this underlying math lets us completely redraw the world from the perspective of literally any nation on the planet.
It's a total paradigm shift. It really is. So our mission today is to uncover the hidden mathematics of our globe, to see how changing that mathematical center literally shifts our geopolitical, logistical, and, well, cultural worldview.
It is a profound shift in perspective. To really grasp this, we're going to ask you to forget that flat rectangular classroom map. Just throw it out.
Toss it in the bin.
Exactly. Imagine the Earth as it actually sits in the dark of space, right? Like a perfect three-dimensional sphere.
Mm.
In our mathematical model today, this sphere has a radius that we will just call r.
Okay, simple enough. R is the distance from the molten core out to the crust. But if the center of the world is just a mathematical illusion created by old maps, how do you even begin to break that illusion?
Right, like where do you start?
Yeah, how do we translate a flat piece of paper into a 3D planet in a computer?
Well, you build a massive geometric scaffold inside the planet. Before we can start spinning the globe and redefining the center of the world, we need a flawless way to identify any location using three simple numbers, x, y, and z. We are essentially building a 3D spatial coordinate system. The absolute center of the Earth, like deep in the core, is our origin point. That is coordinate 0, 0, 0.
Right in the middle of all the magma.
Exactly. And from that burning center, we are going to shoot three conceptual lasers out to the surface.
Okay, let's visualize this scaffold for everyone. So imagine the z-axis as a vertical laser, right? Like a skewer. It starts at the core and shoots straight up through the Arctic ice to the North Pole.
Analogy.
So that point up there is 0, 0, r, meaning 0 on the x and y, but r, distance up the z-axis. And that same skewer shoots straight down through Antarctica to the South Pole. North is positive, south is negative.
That establishes our vertical reality. Now we need the horizontal slice. Our x-axis shoots horizontally from the core out to the equator.
Okay.
Specifically, it pokes out exactly where the equator meets the Prime Meridian, that 0-degree longitude line just off the coast of West Africa.
Okay, so we've got our vertical laser and now an x-axis skewer bursting out of the Atlantic Ocean. The sources mention the front hemisphere, so from 90 degrees east to 90 degrees west, that's a positive x value, while the back half of the globe is negative right.
You've got it. And the final structural piece is the y-axis. This one shoots out at a perfect right angle to the x-axis, also right along the equator, but emerging at 90 degrees east longitude.
Which puts it coming out of the water somewhere in the middle of the Indian Ocean.
Yep, exactly there. Moving east makes y positive. West makes it negative.
So we have this massive 3D crosshair intersecting in the center of the Earth. But, I mean, why go to the trouble of building this invisible framework?
Because this XYZ system translates our historical, somewhat messy concepts of north, south, east, and west into a rigid, mathematically flawless language.
Oh, I see.
Depending on where you are listening to this right now, maybe you're driving down a highway in Ohio or walking your dog in Sydney, your body has a highly specific XYZ coordinate pinging off a satellite.
So this is what my phone is doing.
Exactly. This framework is the foundation for the GPS system in your phone, 3D computer graphics, astronomy, you name it. When a satellite needs to locate you, it doesn't consult a digital paper map. It calculates your physical distance relative to those three lasers crossing in the center of the Earth.
Okay, that makes sense. But latitude and longitude are what we're used to, right? They're basically just angles on a globe. How do we actually calculate your physical distance on this new XYZ grid? Like, how does my phone turn a curved angle into a specific spot in three-dimensional space?
This requires a translation machine, specifically trigonometry.
Trig. Everyone's favorite math class.
Right. But it's super useful here. The sources outline how sines and cosines bridge the gap between angles and distances. Let's break down what those functions actually do conceptually, starting right on the equator.
Okay, let's start there.
If you are standing on the equator, your latitude is 0. You have absolutely no vertical height relative to the center of the Earth, so your z-coordinate is just 0.
So trigonometry is really just the math of circles. Because the Earth is round, I mean, you can never walk in a true straight line. You are always walking along the edge of a giant hoop.
That is a great way to visualize it.
Sine and cosine are just the tools that measure where you are on that hoop. If I'm on the equator, I'm just walking around the widest hoop on the planet.
Exactly. Your x-coordinate tracks your physical movement along what the sources call the cosine circle, and your y-coordinate tracks movement along the sine circle. It's pure, continuous circular motion around the Earth's waistline.
But the moment I leave the equator, things get weird, right?
Mm-hmm.
Let's say I hop on a plane in Ecuador and fly straight north up to Iceland. My position on that vertical Z laser is going way up.
Yep, your height is increasing.
But the physical ring around the Earth at the latitude of Iceland is much tighter than the equator. I mean, it takes way less time to fly all the way around the world at that latitude.
Because your personal horizontal slice of the Earth is shrinking. Mathematically, that shrinking radius is calculated using the cosine of your latitude.
Okay, so as I go north...
As your height, your z value increases, the radius of the circle you can walk around gets smaller and smaller until you hit the North Pole, where the radius is basically 0.
It's like slicing an onion. The slice right through the middle is huge, but the slices up near the top are tiny little rings. Honestly, if I ever made a bet to travel around the world in 80 days, I wouldn't mess with trains and hot air balloons.
Oh, yeah. What would you do?
I'd just fly to the North Pole and jog in a tight 10-foot circle. Bam. Travel the world in 8 seconds.
I mean, you'd win on a technicality, but that simultaneous shrinking of the horizontal radius while the vertical height increases, that is the absolute core of spherical coordinates.
It's just so cool how the math perfectly describes reality.
It is.
Yeah.
And this interplay is the exact mathematical proof of why flat maps always distort the poles.
Because on a flat Mercator map, the top edge of the paper is drawn just as wide as the middle of the paper.
Right. They stretch it out.
They take those tiny top onion slices, those tight circles near the Arctic, and artificially stretch them out to make them look as wide as the equator.
Which is the entire reason Greenland looks roughly the size of Africa on a classroom map, even though Africa is actually about 14 times larger.
Wow. 14 times.
Yeah. The flat map mathematically ignores the shrinking radius of that circle just to keep the paper neatly rectangular.
So the map makers essentially lie to make everything fit neatly on the wall. Okay, so we can turn any latitude and longitude into a point in 3D space using sines and cosines. But the sources highlight that the real power of this math is running the entire process in reverse.
Yes, exactly.
Taking an XYZ coordinate and turning it back into latitude and longitude.
And to do that, the math uses inverse functions. You calculate the arctangent of your y and x coordinates to find your longitude, and the arcsine of your z coordinate to find your latitude.
Wait, let me make sure I've got this. So if sine and cosine pack our physical location into this rigid 3D coordinate box, arctangent and arcsine are basically just the mathematical undo button required to unbox that data back out onto a flat map.
That's a perfect way to put it. It is a perfect mathematical unboxing. You basically reverse engineer the angles from the distances.
But why bother going backwards? I mean, if we already start with a latitude and longitude, why pack it into a 3D box just to immediately unbox it again? What's the point of the extra step?
Because of rotation.
Rotation.
Yeah, once you have converted the Earth from fixed lines of latitude and longitude into a mathematical cloud of XYZ points just floating in 3D space, You aren't bound by geography anymore.
Oh, I see where this is going.
You can physically grab that entire mathematical model and rotate the planet in a computer before you hit that undo button to make it a flat map again.
The sources introduced this concept called rotation matrices. And, instead of getting bogged down in the raw algebra of how a matrix works, let's talk about what it actually does conceptually.
Sure. A rotation matrix is essentially a mathematical command. It's a vast set of instructions that grabs every single point, every mountain and grain of sand on the globe, and rotates it around our XYZ lasers simultaneously by a highly specific number of degrees.
Okay, so imagine spinning a basketball on your finger.
Okay.
Normally, your finger is resting right on the North Pole, and the seams of the basketball spin around that vertical axis.
Mm-hmm.
A rotation matrix is like grabbing the ball, taking your finger off the North Pole, and putting your finger squarely on, say, a city like Seoul, South Korea.
Right.
You are forcing the ball to spin on a totally different axis, recalculating where every other country sits relative to that new spin.
And the sources actually use Seoul as a prime example of this application. If you want to make Seoul the literal mathematical center of your new world map, you take Seoul's current coordinates and you apply this rotation matrix.
You just plug it in.
Exactly. You mathematically force Seoul to shift so it sits directly on the x-axis laser. You command Seoul to become the new 0 degrees longitude.
You just casually steal the Prime Meridian from London and hand it to Seoul. That is wild.
It completely frees us from the historical anchor of Europe being the default center of the world. It is an incredibly advanced cartographic technique that combines spherical geometry and vector transformations to bypass, well, hundreds of years of imperial mapping traditions.
Wow.
Before modern computers, calculating millions of coordinate shifts by hand was nearly impossible, which is why we stuck with the same old maps for so long.
But wait, hold on. Drawing Seoul at the center of the map doesn't actually melt the Arctic ice or physically move continents around? How does changing the layout of a piece of paper actually help anyone in the real world?
That's the big question.
Right. Like if I'm a logistics CEO or a shipping magnate moving billions of dollars of cargo, looking at a Busan-centric map instead of a London-centric map, does it actually reveal anything useful? Or is it just a national ego boost for the country at the center?
Oh, no, it is deeply practical, and it goes right back to how standard maps lie to our eyes. Remember the distortion we talked about with Greenland and Africa?
All right, the shrinking circles.
Exactly. Standard Mercator maps terribly distort great circle distances. And a great circle is the actual shortest physical route between 2 points on a 3D sphere.
Which brings us back to that flight from New York to South Korea in the beginning. A straight line drawn with a ruler on a flat map is almost never a real straight line over a curved globe.
A standard map hides the true distances, but a nation-centered map, derived from pure XYZ spherical rotation, gives you a highly accurate, undistorted view of the aviation and maritime routes radiating out from your specific nation.
That makes total sense.
The math is organized around your location, meaning the visual representation of distance from your port to the rest of the world is finally accurate.
The sources bring up Arctic shipping routes in this context, which honestly blew my mind.
Oh, it's fascinating. Look at a standard map, and the Arctic is this distorted, stretched-out white wasteland across the top. It looks impassable, endlessly wide, and totally unhelpful for shipping.
Just a big block of ice at the top of the page.
Right. But use the rotation matrix to create a map mathematically centered on the massive port city of Busan, South Korea. Suddenly, you see the Arctic not as a flat roof, but as a central ocean basin connecting you directly to Europe and North America.
It completely reinterprets the logistics pathway. I mean, if you are sitting in a boardroom in Busan, a standard map tells you to send your cargo ships south, through the Indian Ocean, up the Red Sea, and through the Suez Canal to get to Europe.
Which takes forever.
But a Busan-centric map reveals that going straight north, right over the North Pole, is a remarkably efficient, direct route. The old map hides that efficiency. The mathematical rotation reveals it.
It reconfigures a nation's entire understanding of geopolitical connections. When you place yourself at the mathematical center of the XYZ grid, your perception of who your neighbors are over the horizon fundamentally shifts.
It changes everything.
It does. It changes economic strategy, it reshapes military planning, and it alters cultural exchange. A shift in the underlying mathematics literally creates a geopolitical shift in the real world.
It is wild to think that something as abstract as a rotation matrix could dictate global trade routes and corporate spending. The tools we use to look at the world quietly dictate our understanding of who is central, who is important, and who is relegated to the periphery.
The key takeaway from these sources is that the Prime Meridian, that 0-degree line running through London, is not an absolute law of nature.
Not at all.
It was a choice made because the British Empire happened to be the dominant naval power when international time and mapping standards were formalized in the 19th century. Mathematics gives us the objective tools to strip away that historical bias and view the world from infinite, equally valid perspectives.
Let's recap this journey because we've covered a lot of conceptual ground today. We started by building a massive 3D scaffold inside the Earth with our XYZ lasers.
The skewers.
Right, the skewers. We learned how trigonometry acts as a translation machine, measuring our position on the giant geometric hoops of the Earth. And we discovered the mathematical undo button, those inverse functions, that allow us to grab the globe, apply a rotation matrix, and put any city at the absolute center of a new map.
We conceptually tore up the map you grew up with and proved that geometry doesn't play favorites. Every spot on the globe is just a temporary arrangement of X, Y, and Z.
Which brings me to a final thought for you to mull over today. We talked a lot about making megacities like Seoul or Busan the center of the world and how that reveals hidden oceans and shipping routes.
Yeah.
But think about your own world. How might your geopolitical worldview, your sense of connection to other cultures, or even just your daily psychological mindset change? If you spent just 1 week looking only at a mathematically perfect world map centered exactly on the town where you were born.
That's a great experiment to try.
Because the math says you have just as much right to be coordinate 000 as anyone else. Thanks for joining us on this deep dive.